I'm Garrick Orchard. I'm also a member of Intel's Neuromorphic Computing Lab. I look at the sensors and perception area and put quite a bit of effort into this performance characterization tool and capability that we have for LuiHi. And this is all available. What I'm going to present now is available to all our INRC members, and the notebook that I will run through is also available as part of our standard NX SDK tools. So I'm going to start off just with a brief one slide of motivation, why we think this is so important, and why we do this type of energy benchmarking. A little recap maybe for those who aren't from such an electrical engineering background, just the very basics in the slide of the different components of power consumption for our chip, and then describe the power states that our LuiHi cores can be in, as well as how NX SDK can be used for benchmarking. And then how we suggest people report benchmark results. It's quite tricky in this field because there's so many different components of power consumption and things to compare against and different metrics that can be used. And then finally, I'm going to describe the application of these tools to a characterization workload where we try to isolate the time and energy required for different types of operations on LuiHi. And then I'll run for that last one. That's where a notebook will come in. So it's a notebook that any INRC users can run through themselves. So starting out with the motivation, why are we so interested in this performance benchmarking? And from our side, coming from maybe a bit more of a corporate entity, we're interested in pushing this technology, to users, and any technology's potential user or adopter or customer, we'd expect to do some kind of due diligence, right? And this due diligence would be some very basic things here. They'd want to verify any claims we're making about the hardware or software or system or technology. They'd want to figure out whether this technology satisfies their requirements. So often they're not just doing it because it's cool, but they have a very specific use case and they need to meet some specific requirements. Otherwise, they're not even going to consider the technology. But further than that, even if our technology does meet their requirements, we're in a competitive landscape. There may be other technologies around that may do an even better job of meeting their requirements. Maybe, for example, perform just as well, but at a higher or lower price point. So they really want to get a clear picture of, can we trust what these guys are saying? Does this meet our requirements? And of the options available to us, is this the best choice for us? So from our side, what we can do is obviously always making sure that our claims are backed up by data and measurements. We want to provide a picture of the technology's capabilities, right? Not just one or two corner cases where it performs really well, but an overall picture where we can highlight strengths and weaknesses of the technology to provide a potential user, adopter, customer with a realistic picture of what they can expect from the technology. And while we'd expect, these users or customers to try to put the technology in context with their other, competing options, we can help them a fair bit by doing some of this work ourselves, trying to compare it to maybe our competitors or prior works, and put the performance in context. Right? So, an amazing power number of X milliwatts, it doesn't really mean much unless you put it in comparison to some other power number that is achieved by some other platform. So this is how I see the problem. This is not the full story behind the motivation. A customer or consumer is going to have other factors in mind, things like cost, ease of use, reliability, availability of the system, all going to come into play. But the point is here that benchmarking and characterization are very important aspects of this problem. Okay, so in coming to how we think about the power consumption on LuiHi, one of the ways we can try to break power consumption down, and this is what from a typical kind of CMOS perspective, is into static and dynamic components. So for those not from an electrical engineering background, this is still pretty simple. Your total power here would just be the sum of your static and dynamic components. The static component is due to leakage currents that flow through your circuits when the transistors are off, or at least when they're not switching. So you can imagine your circuit's in a static state, nothing is changing. You have an off transistor somewhere, but there's still some leakage current flowing through it. So if you see the kind of diagram in the bottom right, it's a simple inverter, and there's this vertical line going down of some leakage that's always flowing. And this is typically temperature dependent, right? So as your system heats up, the leakage current increases. Dynamic energy or dynamic power on the other side is due to transient currents that occur when transistors are switching. So for example, if the voltage at our output there were to switch from low to high or high to low, there's some capacitance there, some charge that's getting dumped onto that capacitor or pulled off it, which means there's some transient current flowing onto or off that capacitor, and there's power consumption associated with that. I'd say that it's independent of temperature. It's not, strictly speaking, it's not really independent of temperature, but compared to the static power consumption, it's far less dependent on temperature. So kind of your basic high school energy and power on the left here. Energy we measure in joules, power is measured in watts. Energy is simply watts times seconds, whereas power is just the rate of energy consumption, so joules per second. And in CMOS, your static power is going to be power times current, so voltage times I leak, and to convert it to an energy, it's going to be voltage times your leakage current times time. Right, so you always talk about energy consumed over some period of time. But for the dynamic power, if you look on the bottom right of that first table, we've got a half CV squared N over T. So the bottom table shows here half CV squared, that's a half times the capacitance times the voltage squared, is the energy required to switch a node once. So if the output switches from low to high or high to low, the amount of energy you consume is a half CV squared. All right. So if you want the total energy consumed by the circuit, you multiply this by N, which is just the number of times that this node switched. And if you want the power, you have to figure out the frequency with which this node was switching, so N over T. Okay, so this is one of the ways that we try and investigate the power consumption. We're interested to know how much of this power is due to static power, which is pretty much just the cost of turning the circuit on and applying power to it, and how much of it is dynamic power, which is due to the computation that's happening. So what you will notice that's interesting here, though, is because we have an asynchronous design, our dynamic energy consumption, a half CV squared N, does not depend on time. It only depends on how many times these nodes were switching, not how long the computation took. Whereas the static component does depend on time, because whether or not nodes are switching, whether or not we're doing any computation, these leakage currents are always flowing. Okay, so that's the static and dynamic breakdown, but another way we can try to break this down is by considering which physical component of our system was consuming the power. So if we look at Luihi, we can break down the system into two different types of cores. So this is kind of a little toy diagram of it. We have this network on chip shown by these gray circles, which are routers. Each of these routers in the top region of the chip connects to four different tiles. Four different cores, which are neuron cores. So a router surrounded by four cores is a single tile. And then in the bottom part, we have the routers connected to x86 cores. So these are the two types of cores we have on Luihi, neuron cores and x86 cores. And we're interested in seeing how much power was consumed by the neuron cores versus how much was consumed by the x86 cores. We don't want to completely neglect the x86 cores because they play an important role in the circuit. But really the neural workload typically is happening on the neuron cores, not so much on the x86 cores. The routers, of course, will also consume some power, but we lump their power consumption into the neuron core power consumption. So we consider the neuron cores plus the energy or power required to communicate spikes and information between them to all be part of the neuron core workload. That's P neuron. And then the x86 is a separate component of power consumption. Okay, so the total power, another way you could break it down is into the neuron core and x86 components. And then we can break down the neuron core component into its static and dynamic components. And on Luihi, so the static power component here is simply the cost of powering the neuron core. So once you apply a voltage to it, this leakage current is going to flow. But we can reduce this by powering down unused cores. Right, so SRAM specifically within the cores can be powered down into a much lower power state that can save you static power. But the core is unusable in this state, right? So if you're not using a core, you can save power in this way. And then there's the neuron core dynamic power consumption. This is workload dependent, right? It depends on your workload as these, bits are flipping from 1 to 0 and back as part of your computation. There's going to be dynamic power consumed. So it's workload dependent, and this is consumed by whatever workload there is, right? Communicating spikes, neuron updates, synaptic updates, all these kinds of things are going to consume dynamic power. All right, the x86 cores can similarly be broken down into static and dynamic components. The static component, again, is simply the cost of powering the x86 core. However, unlike the neuron cores, we don't have the ability to power down an x86 core, right? So in our architecture, at least with N2, the WeHe as we know it today, the x86 cores are always powered. But the dynamic power consists of two main components. There's a clock power. So the x86 cores are synchronous, whereas the neuron cores are asynchronous. So this clock consumes power. And then there's additional power consumed to execute code. So an x86 core is always powered. If you clock it, it consumes additional clock power. And even if it's clocked, it can be either executing some code or it can just be waiting. And if it's executing code, there's an extra power consumed on top of that. Right. We can disable the clock for cores that we're not using, and that saves us a significant amount of power. And obviously, if a core is in the waiting state, it consumes slightly less power as well. So this is kind of all the different components of power that we try to measure and provide to a user when they use the system. So I kind of described it verbally, but to just show it on a plot here, again, this isn't a measurement, but just a kind of cartoon diagram illustrating what the different power states are for WeHe's cores. So starting with a neuron core, if you have a workload running on the system, your neuron cores are going to be consuming some power. I've just called it P neuron here. And it's going to be workload dependent, and it's going to be time varying. You know, if you have a lot of synaptic operations or neuron updates, some point in your workload, or a lot of spikes traveling at some point in your workload, it can cause it to consume more or less power. So in this state, at the top left of the neuron core diagram, the neuron cores are all fully powered and running. However, once the workload finishes, there are no more spikes, no more neuron updates, no more synaptic operations happening. The neuron core is still fully powered, but there's no dynamic power being consumed. So the power consumption will drop by the dynamic power component, and you'll be left with just the static power component. So the neuron cores are still fully powered in that state, but they're paused. We then have the ability to power down the SRAMs, which will drop the power consumption even further. It doesn't drop to zero because there's other logic on the cores that also consumes leakage power, but it does bring the power consumption down for us, a fair degree. So there's these three kind of main states for the core: when it's powered and running, powered and idle, not doing anything, and powered down. The x86 core states can look somewhat similar, but they're a little different. There's also going to be some time varying power consumption while they're executing code. We typically approximate the code as just consuming constant power, but in reality, it would vary a little bit depending on what instructions are being performed on those x86 cores. However, once the model stops running and that core just enters a waiting state, and it can also enter a waiting state in any time step of the WeHe. So say all the neurons are busy updating in a time step, maybe there's a lot of work for them to do, so they're taking a while. The x86 core might have already finished all the code it needs to run for this time step, so it can just enter a waiting state and wait for the end of the time step to occur. In that case, there's no code being executed, so the power consumption drops by that P code factor. Then, so in that state, then the x86 core is fully clocked, but it's waiting for the barrier synchronization process to signify that the end of the time step has occurred. And then once the workload finishes, we could also even turn off the clock, and this would bring the core into an even lower power state where it's just consuming static power. So it's fully powered, but it's not able to do anything because it's not even being clocked. So in both these plots, the top and the bottom, the kind of middle power level is what we'd call the idle power. In both cases, this is the state where the system is powered and ready to go. It just happens not to be doing anything at that point in time. But the moment new data arrives, it can execute code, perform neuron updates, synaptic operations, whatever it might need to be. Okay. So we have some constraints that determine which cores we need to power, when, and why. One of these main constraints is barrier synchronization. Barrier synchronization is a term we use to describe the process by which cores on the chip handshake with each other to signify that the current time step, all computation for the current time step has completed, and they can proceed to the next time step. It's important they do so because, of course, for a neuron to update, it needs to know that it's received all the synaptic information that it needs, or all the spikes it needs to receive in order for it to update itself for the next time step. So if another core is running a bit more slowly and still busy generating spikes, it needs to wait for that to occur before it can do the handshaking and proceed to the next time step. Okay. On a multi-chip system, such as our Nohuku 32 system, which as the name implies, consists of 32 chips, chips that are required by a model need to synchronize their time steps through this barrier synchronization process. So when I say chips required by a model, what I'm talking about are any chips that are implementing any neurons for this model. So if a model requires 10 neurons, it's only going to use one chip, but maybe it needs many neurons spread across many chips, right? This barrier synchronization process has another constraint that it must always operate on a rectangular region of chips. So you can get smart about how you choose which chips to use, but by default, chips are going to be assigned in the order shown here on this diagram. So from 0 to 31. And any Luihi chips that are used must have their first x86 core powered. So in this diagram, we have 31 chips. I've shown 11 chips here with a red background that are used by the model, so the chips 0 through 10. To support barrier synchronization for these chips, we need a rectangular region shown in blue, and all the chips within this rectangular region must have their first x86 core powered, so it can handshake with the other chips and confirm that it's safe to move to the next time step. Similarly, each chip that is involved in barrier sync can have some region of cores within the chip that are operating. So neuron cores required by a model, which again just means any core that's implementing any neurons for this model must synchronize time steps through barrier synchronization. Much like the chip version, the cores require a rectangular region, and it's a rectangular region of tiles. So any tile, remember a tile is a router with the 4 cores around it. If any tile has any neurons that it's implementing, all cores within that tile must be powered. Okay. And we must define a rectangular region, which consists of the first x86 core and any of the neuron cores that are powered. So in this case, again, red is showing the neuron cores we've chosen, but we'd have to power all the cores within this blue rectangular region so that it would include the first x86 core at the bottom as well. Okay, so this just gives you an idea of, we'll automatically power down cores and chips that we're not using, but this is how we select which chips and cores need to be powered on. And it's possible that due to this barrier synchronization process, that we're powering on more chips and more cores than the model is actually requiring. And our tools will try to account for this and remove the static power consumption of cores that we powered but didn't use. The idea being that, of course, Luihi as it stands today with 128 cores is one possible instantiation of our IP, but we could always make a smaller or larger system with a different mesh organization to target a different application. So we try to report the total power consumption of the system. We try to tell you how many cores were turned on, and we try to tell you that if you were able to turn off the cores you weren't using, then what would your power consumption be? So this is a brief overview just of kind of the very basics of power consumption, how we break it down, and how we have to power all these different parts of the system and synchronize them. Then it comes to how you'd actually use our power tools, right? So our NX software development kit is in Python, and you typically define some kind of a model that you'd want to run. You'd compile this model into a board object, and then you'd call a line of code that looks something like this line above. We'd call board.probe. You tell it that you want to probe energy. So that's the probe type equals probe parameter.energy. And you can attach some probe conditions. So when you want to start and stop probing the system, and this is runtime in terms of Luihi time steps. And then buffer size and bin size control kind of the size of some buffers that are used by the x86 cores on Luihi. And bin size is just a factor by which we combine measurements into single measurements. So for example, we might want to combine a series of 8 measurements or time measurements into a single average measurement to have a more compact representation in memory on the x86 core. When you do this, when you call this line of code and you run your model, you're going to see kind of a power profile that looks something like this diagram at the bottom. So when your workload's running, you're going to see this time varying component of power consumption. When your workload stops, you're automatically going to drop, the power is going to drop by the Neuron Core dynamic power component and the code power component. You can then power down the clocks for the x86 cores and see another drop in power. And then you can power down the SRAMs for the cores you're using and see yet another drop in power. And by having knowledge of the relative sizes of different SRAMs in the system between the x86 and Louis cores, but by knowing kind of the ratio of the area of the chip that's used by SRAMs and used by logic, we can extrapolate to estimate how much power was consumed by different like logic and SRAMs in different parts of the system. I'm not going to go into all the details of that, but if you are in the NX SDK, we do have a white paper that is available to you that does go into details, provide you all the equations we use as to how from following this procedure of shutting down in the sequence and measuring the power while we do the shutdown sequence, how we go from that to estimating the actual power consumption of the system and its breakdown by static and dynamic, Neuron Core, and x86 components. So from a user's perspective, you run this line of code at the top, you run your model, and the NX SDK is going to return to you a dictionary called Power Profile Stats, which will tell you a whole lot of information relative to the run you just executed on Louis. So it's going to tell you the number of x86 cores that were being clocked, the fraction of time during the run that each one of these cores was executing code, the number of chips that were turned on to support barrier synchronization, how many neuron cores were turned on to support barrier synchronization, were used by the model, how many were supporting barrier synchronization, what the average duration was for every time step on Louis. So because we have this asynchronous architecture, and because the cores all do this handshaking at the end of every time step, they're free to take as long or short as they require to finish their computation for a given time step. So the time per time step can vary. And at the end, we just report to you this average time step duration. You can get the per time step times as well. They are available to you, but this is just kind of like the high level summary that we provide. And then last, we provide this power, which is a dictionary of the power numbers described on the next slide. So total systems, total, static, idle, and dynamic power. And then the core part of this dictionary gives a breakdown of the dynamic and static power consumption components for the neuron cores. And then lake mount, which is kind of just another word we use to refer to the x86 cores, will tell you the power consumed by code execution, the clock, total dynamic power, which is just the sum of code and clock power, and then the static power consumed by all the x86 cores. Okay, so I've given an overview of the different parts of the power consumption that we try to measure and what it would look like from the tools to run a test like this on some model that you've set up and what the tools will return to you. A couple of things that we'd want people to look out for when running a model. I'll go into the next couple of slides. So this first shows just an example of a good power measurement. You set up the board, you run your power tools. As the board starts running a model, the power consumption jumps up to some higher level. And hopefully it's relatively stable and flat while your model is running. You measure power during this time. And at the end, we have the stage shutdown sequence, which we use to break down the different components of the power consumption. But there are some pitfalls you can run into. Things like a startup transient maybe started measuring power just when the board was booting, but then because you have a long setup time when you're not doing much, you could have the startup transient where your power is below kind of your model's total power consumption. And this is, unfairly makes Louis look better than it is because it's going to drag your power consumption down and make it look lower power than it is. And another part is that the x86 cores are tracking the duration of every time step during your model's run. And they have to store all this information in internal buffers. And if those buffers get full, those x86 cores have to pause the whole system and then offload those buffers, to an external host before the system can continue. And doing that, pausing the whole system, means the x86 cores and, all the neuron cores are paused, which means they're not consuming power. So you'll see these dips in your power consumption. And correspondingly, you'll see these spikes in the duration of every time step. So it just means that there was a time step, if you look at the bottom plot, there was a time step, or 4 in this case, where the whole system paused, and it took very long to move to the next time step because the x86 cores had to empty these full buffers. So you can easily check these kinds of conditions, but these are the sorts of things that you'd want to watch out for. Another thing to watch out for is many of the models people run on Luihi are very small, and Luihi can run very fast. Our power measurements have some time constants to them, right? The components in the system can take on orders of milliseconds to stabilize on a new power level. So if you're running a model that only runs for a millisecond on the chip, your power is never going to ramp up to its steady state, and you're not going to get an accurate power measurement. Another problem is that if you're running a model of 100, 1,000, maybe 10,000 neurons, this is tiny compared to a 32 chip system, right, where you can do 100,000 plus neurons per chip. So you need to make sure that your model is reaching its steady state power consumption, and then that power consumption is significant compared to the baseline power consumption for just turning on a 32 chip board. So we do our best to break these components out for you, but if you're consuming 1 milliwatt on top of like a 1 watt baseline for powering 32 chips, then even noise in that 1 watt baseline is going to be a larger magnitude than the 1 watt power you're consuming, and can make accurate measurements of that 1 watt very challenging. So you typically overcome the top problem by having your model run repetitively in a loop, so that it runs for a long time and reaches some stable power level. And you'd overcome the bottom problem if you have a tiny model by replicating this model many, many times across a chip, across a core, across a chip, across a system. So an example here is something that Sumit put together for the Slayer models. Many of these models are quite small. So we have, say, 3x86 cores per chip shown in these red blocks. They're injecting spikes into a copy of the model, which is shown in this bluish color. But then we'll instantiate multiple copies of the model on a chip. And then we'll repeat this across all the chips in the system. And the more we do this, the more copies of the model we have running, the more power we're going to consume. But of course, we divide that total power by the number of copies of the model that we're running to get an estimate of the power per copy of the model. And this can help us to kind of average out the noise across all these different copies and get a much more accurate estimate. Once you have an estimate of power consumption, you'll need to report your results. We like to focus on the energy delay product. This is a metric of the architecture. Depending on how you define it, it can also be a metric of your algorithm. But the reason I say it's a metric of the architecture is that it's possible to skew this metric, or if you have, let me take that back. If you have a metric that focuses only on energy or delay, you can skew them. You can run circuits at high voltages to allow them to switch faster. Right? So if you want to optimize for delay, if you want to decrease your delays, you can apply a higher voltage and get a faster system. But it comes at a cost, right? For example, increasing the voltage increases your energy by a factor, or your dynamic energy or dynamic power by a factor of the voltage squared. So if I were to focus only on latency, only on delay, sure, I can make my system fast, but I'm paying this, power of 2 price in terms of power. On the other hand, of course, I can do the opposite. I can drop the voltage down to save power. I can talk about how amazingly low energy my system is, but it's going to take a long time to do anything, right? So if you multiply these two factors together, it tells a far more complete story of the product of energy and delay. And you can still play with the trading off the delay and the energy by messing around with, say, the voltage. That's fine. But if you take this product of the two, you're always kind of capturing that trade-off of where if you bump one up, you're bumping the other one down, and vice versa. So we like to focus on this energy delay product because it tells a far more complete story of the architecture. In some cases, people will incorporate delay not just to mean how long it took the architecture to run a given number of time steps, but maybe to reach a correct classification result on a task. In that case, you're also incorporating some element of the algorithm, right? A more accurate algorithm may be able to reach a solution sooner, and we can count that as part of your delay in the system. We typically, when we're reporting benchmark results, want to report them in a form something like this. So for this presentation, the slides I'm showing here, we always want to report the system that we were using, the software that we were using, the physical hardware, Luihi system that we were using, and then a disclaimer at the bottom of when the results were recorded. And a standard disclaimer we put on all our results, which are that our results may not reflect all publicly available security updates, and results may vary. So in this case, you can see what our hardware was there: 24 GB RAM, Intel Xeon. This is actually a shared system that we all use. It's not like we dedicated just for benchmarking. so probably overkill in this particular case, but nevertheless, for the sake of completeness, it helps show what that system is. The software we were running, the specific version of the NX SDK we were running, we were always trying to improve the power benchmarking tools. And so depending on what version of the software you were using when you made your measurements, you may get different results. So it's very useful for us when we see a benchmark result to be able to know which version of the tools were used, so we know which improvements were included, and we can kind of do a fair job of comparing back to it. And then which hardware system we're using for Luihi. So our Nahuku 32 chip system was used here. And here I'm referring to NCL-GHRD04 is a specific Luihi, Nahuku 32 board. There can be slight variations even between boards, and therefore, for the sake of completeness, it is useful for a user or someone else who's trying to compare their results to know exactly which board you are using. Just through, natural variations in manufacturing, both to the silicon and the PCBs, sometimes it's possible to run some boards slightly faster or slower than others. And so it's useful to know which one is being used. Okay, so on top of the disclaimers and being concrete about, what system was used for the measurements, we also want to talk about what results should be reported. Different people may focus on different metrics depending on what is valuable for their specific task. That is fine. There are many possible ways you can measure power consumption, but we really encourage people to just report as much information as possible. If you have to put it in an appendix or something, that's fine, but just putting all this information down covers all your bases, right? It's not that there's one correct or one wrong way or many wrong ways of reporting power consumption. It's that you're publishing a paper, you're publishing a report, and other people are going to come back later and they're going to have a different idea, a different aim, a different algorithm. They're going to put importance in a different metric, and they want to be able to compare to what you did, evaluate, how did your algorithm perform on the metric that's important to them? So providing as much information as possible is really useful. So as just some kind of starting template you could use, you'd say that the model, whichever model it is you ran, occupied some number of neuromorphic cores. This is giving an idea of the kind of silicon area that is required for this model, and then how long it took to complete. And so the duration can be different. How you define the duration can be different depending on your task. If you were trying to simulate the brain, you might say you just want to know how long does it take to simulate a single time step of neuron updates. If you're doing something like a deep neural network task, maybe you just want to know how long it takes to classify an image. Maybe it's something else. Maybe you need to process a sample. Maybe you're not doing classification, but there's some kind of other kind of data or sample that you want to process. And you just want to know, I don't care if it took 100 or 1,000 time steps. I just want to know how long did it take to finish processing the sample. So you choose some duration. This is going to be your delay component, right? How long that took. And then you give a breakdown of how much energy it consumes, hopefully a breakdown of both the static and dynamic components, and finally the energy delay product, right? So be clear about what delay you're using and which energy components you're using, but you'd report this EDP, energy delay product. And then again, the standard wording just about which system you are using. And then table 3.3 here, this is from kind of the white paper that we distribute within the within the INRC. Table 3.3 shows something that you can include that shows a breakdown of energy consumption into these different components I've been describing, but has the addition of two different comparison points, comparison A and comparison B. So again, a user or adopter of this technology is probably very interested in knowing Luihi's power consumption, but wants to see how it squares up against other devices. And this is really tricky, right? This is the point where trying to compare to a GPU or something else that has a completely different operating principle can be quite difficult. And you're just going to try to do the best you can here to provide some kind of context for this result, but also provide as much detail as you can in the top part of the table so someone else who wants to compare to maybe a different comparison architecture or a different neuromorphic architecture or whatever it might be can come and take your results and use them. Okay. So this is getting to the end of just the power benchmarking part of it. For those who are in the INRC, you can get access to our performance and energy benchmarking white paper on Confluence, and you can go look at these paths within our software development kit. We have tutorials on performance profiling, and then the second, we have this module on characterization. I'm going to jump into that module next, which is how we apply these tools to try to estimate the energy and time for specific operations on Luihi. But I'm going to pause for just a second and see if there are any questions in the chat. if I can find the chat, I may have to.
Yes, I've been already quite busy answering some questions in the chat, but
would you like to ask some there? Yeah.
I guess should we read the ones that have been answered already? People had some questions about whether barrier synchronization causes bottlenecks, and we try to explain that this is not necessarily the case. There are some impacts, but it doesn't really matter that much.
Yeah, I mean, barrier synchronization does not occupy a lot of time. The only time it's going to be anywhere near a dominant time factor in the system is when you have a model that's doing almost nothing, right? As soon as you have a couple neurons being simulated per time step, your barrier synchronization time is not really going to be your limitation anymore, right? So sure, if the system's doing absolutely nothing else, barrier sync is going to limit you, but typically it's not the limit at all.
Usually the limit will be communication spike traffic between cores and chips.
Yeah, so there's a trade-off there. The communication gets bottlenecked because as spikes arrive at a core, it has to implement a lot of synaptic operations, which take time, and that can back pressure into the mesh, and then you have a back pressure of spikes unable to get to where they need to go. So yeah, on any decently sized model, that's probably one of the limitations you're going to run into. That's, especially if it's a multi-chip model where there's maybe just one link between two chips, and all cores on one chip that want to talk to another chip have to go through the single link, and this link is slower than the on-chip links because it's going, through PCB wires versus, on silicon connections. That can turn into your bottleneck. But even on something like a large, Nahuka 32 system where you have 32 chips doing barrier sync, the time is pretty negligible.
There is one current question left that I haven't answered yet, which is about whether the x86 in unoccupied chips shut down completely, or whether a small amount of static power will remain in this case.
So we do not have a way to turn off the x86 cores or power them down. We can turn off their clocks, and I can tell you that their clocks consume more than an order of magnitude more power than the static consumption of the core itself. These cores are tiny compared to the neuron cores. We don't have a way to shut them down, but it's not really a problem for us. There are only 3 of them per chip. They're tiny. Their static power consumption is negligible.
I think that's it for now.
Okay. Well, with that, so let me go into an example where we'll provide, a basic workload that we run and some numbers that come out of it. So this characterization workload uses a simplified Louis processing pipeline. What I mean by that is Louis, if you want to go read the papers, or if you're in the INRC or something, it has all kinds of different features you can use. It has a lot of, say, sharing features where you can share synapses between different connections, axons between different connections. It has on-chip learning capabilities. It has all kinds of, pseudo-random noise capabilities, stochasticity, delays, many, many features. In this case, we're throwing most of that out the window, and we're looking only at a very simplified Louis processing pipeline, which is kind of the most fundamental operations that you'd want to perform in a spiky neural network. And the model is that you have dendrites feeding into neurons, shown on the left on a source core. These neurons, if they exceed their threshold, generate spikes. These spikes travel via axons to destination cores. I've shown 3 destination cores here on the right. When they reach the destination cores, these spikes look up some number of words in the synaptic memory, and each word in that synaptic memory can have some number of synapses inside of it. Those synapses are read out and so-called implemented, or the synaptic ops associated with them are implemented to update the dendrites, and that dendritic input would then feed into the neurons on the destination cores. To simplify the process, for this workload, we don't have any dendritic input on the source cores. Right, so the source neurons are operating only under an internal bias. There are no synaptic operations or dendritic inputs happening on the source core. And on the destination cores, we don't actually implement any of the neuron bodies. We only take the computation as far as updating the dendrites. Right, so this The reason for that is that we can isolate all synaptic operations to the destination cores, all dendritic operations to the destination cores, and all neuron updates to the source cores. A different view of this processing pipeline and the parameters that we use in this workload are, for every source core, we're going to have some number of neurons. In Loihi, we can have up to 1,024 neurons per core. So this is a parameter n. We're going to vary the number of neurons in the source core from 1 to 1,024. Each one of those source neurons can index some number of output axons from 0 to 1,023 different possible output axons that could be indexed. So we can vary how many spikes are generated by varying how many output axons are associated with each neuron. Spikes will leave the source core, traveling to the right, and traverse D router hops. So this is D is just for distance, some number of router hops from left to right to reach a sync core shown on the right. Each spike, when it reaches a sync core, is going to look up some number of synaptic memory words, W for word, just the number of words. And each one of these words is going to contain some number of synapses, in this case from 1 to 38. In practice, Loihi can support even more synapses per word, but in this case, this was the range we used. So these are the 5 main parameters we're going to use. There's one more parameter, which is just how we bias the source neurons. So the source neurons can be in one of 3 main states. Either they're off in a kind of power gated state, so not the SRAM's powered down, but they're not active, they're not updating, so they're kind of almost skipped over during the updates. They can be in a state where they're biased, which means they're updating, but they're not biased strongly enough to cause them to spike. And they can be in a third state where they're biased strongly enough that they spike on every time step. So those are the different states that a source neuron can be in. And then through these parameters on the slide, N, A, D, W, and S, by varying them, we can isolate different operations within the chip. We're going to replicate this workload as many times as possible across the whole Nahuku 32 chip system. So how do we do that? Well, inside every chip, we're going to have a whole lot of source neurons on the left, shown in this region in blue. And then we're going to change where we place the destination neurons, which are the green ones. We can shift them from left to right to control the number of router hops that spikes travel between a source core and a sync core. And this is all there is to the workload. We can then vary these things. So for example, we can run into a case where we set A equals 0, which means there are never going to be any output spikes, and then just vary the number of source neurons, and using our tools, measure the power consumption of the system, and then estimate the power consumed, the time duration of each time step. From that, we can get an energy per time step. We can break that further down by knowing the number of neurons into an energy per neuron update and plot it. Okay, so how do we do that? Here's an example of plots for the 3 different states I described for neurons. On the left, and in this case, you're measuring the time duration for a single time step on Loihi. Okay, so in this case, we're implementing some number of neurons per core. Remember, all the cores are operating in parallel, so what we're interested in is how many neurons are updating on every core. And as we sweep the number of neurons on the core from 1 up to 1,024, we see the time per time step increase. So the amount of time Loihi took to implement this workload can increase from about 4 microseconds to just over 10 microseconds. By fitting a line to these data points, we can come up with a slope, and we can see that the slope here is that the time duration per time step increases by about 6.1 nanoseconds per neuron update. This is in the inactive state, which is kind of a power-gated state. The neurons will start updating, but soon realize that they're in the state and move on to the next neuron update. In the middle, we have idle neurons. These are neurons that are performing the full update, but they don't spike. So the time per time step you can see here varies from, again, just over 4 microseconds to just over 14 microseconds. The slope is a bit steeper. Unsurprisingly, it takes a little bit longer for us to perform neuron updates in this idle state. And then on the far right, if neurons are in the spiking state, this increases even further the slope to 38.9 nanoseconds. So spiking neurons consume considerably longer amounts of time per neuron update than idle or inactive neurons. to answer the question about barrier synchronization, well, you can get an idea here. If we're able to perform this many neuron updates in, in the region of say 4 to 10 microseconds, and that includes barrier synchronization, you can get a feel for the fact that the barrier synchronization is typically not a huge factor for us. Okay, of course, we're not just interested in measuring the duration of each update. We also want to measure the energy required, which is going to be the power that we measure times the time step duration. And then we're going to compute a slope similar to what we did for the duration. So on the left, again, we have the inactive case, but this time, instead of plotting the time taken per time step, we're plotting the dynamic energy consumed per time step in microjoules. And we get pretty clean measurements here. You see a pretty linear increase with the number of neuron updates performed. And we can give numbers here, as you can see on the top of each plot. Again, I've put the slopes that we've fitted to these lines. Sorry, the lines will be fitted to this data. And so the slope on the left, 47.5 picojoules per neuron update, increases unsurprisingly for idle neurons, and again, increases for spiking neurons. We can do other things too, like varying the number of synaptic updates we perform. So just by changing the number of synapses in every synaptic memory word, we can keep the rest of the system the same. There's the same number of neurons, same number of spikes, same number of synaptic memory words, same distance traveled by spikes, but we're just varying for each word that's read how many synapse updates are performed. And again, we see a pretty clean increase. It looks quite linear here from 4 nanoseconds to 4 nanoseconds and 21.1 picojoules per synaptic op. Right. There are far more plots available in our white paper, but at the risk of boring you all with those details, here's kind of a summary that just puts those slopes together. So we have a few different things that we measured, shown there on the left. We have measured, which are the middle two columns, the latency and energy for the different operations, actual measurements from Louis. The star there says see backup for workloads and configurations. Really, I covered this already. It's just the systems that we use to take these measurements and the versions of the software. On the right-hand side, we have estimates. These are from an old paper. You can look at Mike's 2018 IEEE micro paper. These are kind of some pre-silicon estimates of the latency and energy. And to our relief, these look like they align pretty well with the estimates we had. So finally, I'm going to switch over just to a notebook here. So this notebook, the time and energy per operation, is available to all our INRC users. I'm going to just restart it here. I'm not going to go through all the boring details of this notebook. I'll highlight maybe just one run through of a particular set of operations. The point here is to highlight that this notebook is available to INRC members. If you have access to our NX SDK, you can just go find this. It's released to you already. You can run it yourself. You can play with the different systems. You can play with the different parameters and see the results you get. So this is just, this top part here is just describing the slides that I've already presented to you. Again, we just have to import our NX SDK. In this case, we're going to run on a specific system here called NCL GHRD01, and every simulation is going to be 100,000 time steps. This one measures the number of neuron updates that are performed per core. Typically, the commented out code that you see at the top here, we do a bit more thorough of a sweep. But in this case, for this tutorial, I'll probably let's just do 3 points per different type of neuron update. So I'm only going to do 3 because it'll save a lot of time. But you can go and put as many as you like in that array and run it. It's going to loop over here the 3 different possible neuron states, which are inactive neurons, idle neurons, or spiking neurons. For each one, it's going to run a simulation with a different number of neurons per core, which are the 1, 256, and 1024 cases. And then afterwards, with the data points, it's going to plot the different number. Sorry, let me get this started. It's going to plot the different number of, so it's going to plot the data, do a fit, and tell you what those results are. So down here, we see we're kicking off a run for the inactive neurons per core. In the background, it's busy booting up the Louis system. So it's configuring. This is going to be running with this workload replicated across all the different rows of our Louis chip. And it's going to be replicated across all the chips in our Louis 32 chip Nahuka 32 system. So it's run, it's implemented that power shutdown sequence. finished, and now it's gone on to the next one. So here it's measuring 256 neurons per core. Should take a little bit longer. Typical processes here you're seeing are it's booting up, it's compiling SNPs, which are basically the C code that runs on the x86 cores. It's configuring all the registers of the chip for the run. It runs, and then afterwards it has to pull all that energy and time measurement data from the x86 cores and from the host, and then process these time series of data to extract the information that we're looking for. Okay, so now it's running the 1024 case. For the inactive neurons, after this, it should spit out a plot and then move on to measuring the same thing for the idle case. Okay, I'll come back to this, but you can see similar things here, like here we vary the number of output axons per neuron. Oops. We vary the number of output axons per neuron. You can do the same thing, and you get a similar plot. Again, you'd normally have far more dots on this line here, but in anticipation of this tutorial, I've just kind of culled the number of parameters down. The spike distance, again, how many tile hops must be traversed by every spike. Can give you similar kind of numbers here. But let me go up to inactive case here. We measured 6.1 nanoseconds per neuron update, 48.4 picojoules, and this should hopefully correspond pretty well with what I put up over here, which was 6.1 nanoseconds for inactive neurons and 47.5 picojoules. So very small difference there in the in the energy consumption per neuron update, but a pretty good agreement. And again, this notebook will continue running for all the cases, just to follow through to its completion. The final one is, final two, the number of synaptic memory words we read, and the number of synaptic operations that are performed. So again, we release this to all users. Anyone is free to go and play with this as you wish. With that, while we watch it proceed, I'm happy to take a couple questions.
There was one question we missed earlier in the chat where Sven Nietzsche was asking whether the voltage scaling was that you explained in the very beginning was purely theoretical, or whether this is actually a parameter we can touch and change in LOE to make it run faster or not.
It is a parameter you can change in LOE to make it run faster. We don't really expose this in a very well supported manner in our NX SDK today, at least not. It is well supported if you're running things at a very low level, but if you're kind of operating at a higher Python level, it's not so well exposed. But certainly if you're running at a low level, you can manually specify, it is possible to manually specify what voltages are used for the chip. Now, it should be clear here, as I think anyone with an electrical engineering background will know, that there are certain bounds though, right? So if you exceed certain parameters, that things are going to stop working. For example, if you're clocking your x86 cores at a certain rate, a certain clock frequency, but you lower the voltage so much that they slow down so much that it can't finish an operation within a clock period, you're going to start seeing some failures. And on the other side, if you start running things far too fast, you could run into some, timing or power problems as well. We don't have active cooling on our systems. Of course, the whole idea is that these systems are low power, so you don't need active cooling. But as you start trying to bump that power consumption up or that voltage up, your power is going to increase as a factor of V squared. And as your power increases, that power is dissipated as heat. And as you heat up the system, the power further increases, and you can end up with a kind of a runaway thermal situation, which, I mean, the chip is just going to stop working and start again. But if you're taking power measurements, you kind of want to know that you're measuring power on some useful workload, not on some chip that's just halted because you somehow managed to overheat it by you passing in an incredibly high voltage.
Yeah, I think our default settings are such that the chip will run as fast as possible in a safe way.
Yeah. Yeah, there are different voltages that you can change, and I guess different parameters you can change to control speed elsewhere on the chip as well, particularly in the communication between chips. And there we do tweak them to try optimize them on a board per board basis.
What might be useful perhaps is if you're running maybe Louis in a real-time environment, I don't know, robotics or so, where, I don't know, you want to basically clock it and run it with 1 millisecond per time step or so really slow it down, that in that case it might actually make sense to even lower the voltage because you just don't need to run that fast.
Yes, exactly. So for things like what Sumit was presenting, the devious gesture case, I've been showing numbers here of us processing a single time step of data, which in the DVS case is about a millisecond of data, just because there's no need for us to process that data at microsecond or 10 microsecond resolution. Millisecond is ample. I mean, if a person's waving at you, it takes many milliseconds for them to just move their hand far enough for you to know that they're waving. So, doing thousands and thousands of updates within a millisecond is just completely unnecessary. So in that case, we typically use the x86 cores to slow the system down. And what I mean by that is, remember there's this barrier synchronization process. So all the neuron cores will do all their updates. The x86 core will finish all the code that it needs to complete. And then the x86 core will very intentionally wait for the end of the millisecond before it completes its handshaking with the cores and allows them to continue. And during that time, there's just nothing happening except static energy being consumed within the system. So lowering the voltage in that case could save you significantly on the static energy part. And if the update took whatever the factor is, if it took 100 microseconds instead of 10 microseconds, or if it took 500 microseconds instead of 100 microseconds, it'd still be well within your requirements of 1 millisecond. So it'd kind of be transparent to the user. Okay, I think we're approaching or even at the time.